Hi, everybody. In part one of this lecture, we ended by defining what n factorial was, where n is any positive whole number. And we found out that n factorial is n times every positive whole number less than itself. Now, there's a reason why we have to know that definition. And in part, it involves something called a permutation. Mathematically speaking, a permutation of a set of n objects is an ordered arrangement of the n objects. So a permutation of a set of n objects is an ordered arrangement of all n objects. Let's look at some examples. Consider the set that has two elements, 1 and 2. There are exactly two ordered arrangements of this set. We can either have the objects listed as 1, 2, or we can list them as 2, 1. Those are the only two ordered arrangements of a set that has two distinct elements. Two arrangements. Now let's consider the set of elements 1, 2, 3. Three distinct elements. It turns out that there are 6 ways of ordering these arrangements. There are 6 ordered arrangements of the three objects. We can have 1 as the first element, and then the other 2 elements we can list as 2 and 3, or we can have 1 as the first element and list the other 2 elements as 3 and 2. Those are the only 2 ordered arrangements in which 1 is the first element. Well, suppose 1 isn't the first element. Suppose 2 is the first element. Then we can take the other 2 elements, 1 and 3, and either arrange them as 1 and 3, or we can take 2 as the first element and arrange the other 2 elements as 3 and 1. Those are the only 2 ways that we can order the 3 elements in such a way that 2 comes first. Well, maybe 1 isn't the first element, maybe 2 isn't the first element. Maybe 3 is the first element. And if 3 is the first element, we can take the remaining elements and order them this way, 1 and 2. Or if 3 is the first element, we can take the remaining 2 elements and order them this way, 2 and 1. And that exhausts all distinct ways of ordering these 3 arrangements, these 3 elements, rather. These are all the distinct ways that we can order the 3 elements. And we have 3, no we don't, son of a gun. We have 6 arrangements and before we try to arrive at any conclusion, let's look at one more example. Now, how many different ways can we order the elements of this set? just one. One comes first, and we've ordered all the elements. There's exactly one ordered arrangement of the objects in the set, and here it is. One arrangement. Now, if we look at this, one element, one arrangement. Two elements, two arrangements. Three elements, six arrangements. There might not be any bells going off in our head, but maybe there are. Isn't this equal to 1 factorial? And isn't this equal to 2 factorial? And 6. We have a set with 3 elements. We have 6 arrangements. But 6 is 3 factorial. 3 times 2 times 1. And we might wonder if this is just a coincidence or whether this pattern holds for any number of elements in a set. See, we had one element and there was 1 factorial arrangements. We had 2 elements. There were 2 factorial arrangements. We had 3 elements. There are 3 factorial arrangements. And the fact of the matter is, this is not a coincidence. This is the general pattern, and I will write that down. And then we'll look at it logically so that we can understand why this pattern holds. Here's the scoop about permutations. Let n be any positive whole number. Given a set of n distinct elements, there are n factorial distinct permutations of the set. And let's see why this is true. Let's just take the set of elements, 1, 2, 3, n minus 2, n minus 1, n. Let's just take a set of n elements, and we'll just say that they're 1, 2, 3, 4, 5, 6, all the way up to n. And we have an element that can be put or selected first. And after we've selected that element, there's going to be a second element. Whoops, whoops, whoops. After we've selected the first element, then we select the second. And after we select the second element, then we select the third. And so on and so forth. The last element selected is going to be in the nth spot. The one selected before it will be in the n minus first spot. And the one before that will be in the n minus second spot. We're going to pick the element that goes first. How many different elements can we choose from to pick the first element? Any of these n elements can be first, can't they? So there's n different ways that we can choose the first element. Or when we choose the first element, there are n distinct outcomes. And then we choose the element that comes second. How many elements can we choose to go second? We can choose all of these n elements except the one that we put in the first slot. We've used one of the elements, so there are only n minus 1 elements left to put here in the second spot. So we've chosen the first two elements. We're going to choose the element that goes third, and it can be any of these elements except for the two that we've already selected. So in the third spot, we can take any of the unselected elements. And how many unselected elements are there? Well, we've selected 2 already. So there are n minus 2 elements that we haven't selected. So n minus 2 elements remain. And one of those n minus 2 elements will go in the third slot. When we get to the next to the last slot, there are 3 elements that have not been chosen. So any of those 3 elements can go in this spot. When we get to the last spot, there are 2 elements that haven't been chosen. So either of those 2 elements can go in the next to the last spot. And when we get to the last spot, we've already selected every element except 1 to go in the first n minus 1 spaces. So there's only 1 element that we can put here. Now, what is this? If you think about it, it's an n-stage experiment. The first stage is that we pick the element that goes first. The second stage is that we pick the element that goes second. The third stage is that we pick the element that goes third, and so forth. And there's n ways that we can pick the first element times n minus 1 way. I'm sorry, let me do this a different way. There are n outcomes for the first element times n minus 1 outcomes for choosing the second element times n minus 2 outcomes for choosing the element that goes third, dot, dot, dot. 3 outcomes for choosing the element that goes next to last, times 2 outcomes for choosing the element that goes next to last, times 1 outcome for choosing the last element. So the number of outcomes for this n-stage experiment is the product of number of outcomes for the first stage times number of outcomes for the second stage, and so on and so forth. And that's going to give us n times every whole number less than itself. So the number of distinct permutations or the number of distinct arranged orderings of a set with n elements is n factorial. This is a good one. 10 horses are entered in a race. In how many different ways can the 10 horses finish? This is an ordered arrangement or a permutation of a set of 10 distinct horses. Every horse is going to appear once and only once in the ordering. So every horse appears exactly once, somewhere in the ordering. We have 10 horses. There are 10 factorial permutations of how they can be ordered or how they can finish. And son of a gun, let's see, do I know what this equals? $3,628,800. There are only 10 horses, but these are the number of distinct finishes that can occur with just 10 horses. Yikes. I'm glad I don't have to write out every single possible outcome. Can you imagine that? I don't know much about horse racing, but I know enough about horse racing to know that the order of all 10 horses is not relevant. In horse races, typically, if a horse doesn't finish first, second, or third, then it's of no consequence. A horse only pays money if it finishes first, or if it finishes second, or if it finishes third. So I guess what you can do is you can wager money on the horse finishing first. You can wager money on the horse finishing second, or you can wager money on a horse finishing third, or you can wager money on a horse to show, which means it's in one of the top 3 spots. At least that's my understanding of it. So in such a case, people who are interested in the outcomes of horse races are only concerned with 1, 2, 3 finishes. They're not concerned with anything else. So this is a relevant question. 10 horses are entered in a race. How many different 1, 2, 3 finishes are possible? And I think we should do this two different ways. We'll do it without using permutations. And then we'll introduce a rule using permutations that will allow us to get the same result. If you think about this, this is really a 3-stage experiment. The outcome of the first stage the horse finishes first. The second stage, a horse finishes second. The third stage, a horse finishes third. And think about this. Can one horse finish both first and second? No. If a horse finishes first, it can't finish second. If a horse finishes second, it can't finish first. If a horse finishes first, it can't finish third, and so forth and so on. So really, this is a three-stage experiment in which we're selecting objects or elements from a pool of elements. We're selecting horses from a set of 10 horses. And since a horse can't finish both first and second, when we select a horse to finish first, we take that horse and we put it in our pocket, so to speak. The horses are being selected without replacement. Stage one, the horse finishes first. There are 10 different ways that this can happen. Any of those 10 horses can finish first. Now the second stage, a horse finishes second. One of the 10 horses has finished first, so how many horses are left to finish second? 9, right? The first 2 horses have finished the race, and now we're looking for the horse to finish third. How many candidates are left to finish third? The horses that finished first and second can't finish third. So there are only 8 horses left which can finish third. So the total number of outcomes for 1, 2, 3 finishes is N1 times N2 times N3. And that's going to be 10 times 9 times 8, which equals 720. Now, I said I wanted to do this 2 different ways. We're going to do this again using another counting rule. Here's the counting rule that we need to do our previous example a different way. Given a set of n objects, suppose that r objects are to be selected from the set of n objects. The number of permutations of r objects selected from the set of n objects is denoted NPR and is given by this formula, n factorial over n minus r factorial. And what this is the number of permutations of r objects selected from a set of n objects. The number of permutations of r objects selected from a set of n objects. And that turns out to be n factorial over n minus r factorial. Now let's apply that to this example. Here's our example. 10 horses are entered in a race. How many different 1, 2, 3 finishes are possible? And of course, when we talk about a 1, 2, 3 finish, order matters. So here's what we're doing. set of 10 horses, we're selecting 3 horses. And those 3 horses are going to be ordered. First, second, third matters. So what this is a permutation of 10 objects. And we're selecting 3 objects from those 10 objects. It's a permutation of 10 horses. Or let me say it this way. It's a permutation of any 3 horses selected from a set of 10 horses. And from this formula, n is 10. So we're going to get 10 factorial over n minus r, 10 minus 3 factorial. And if we have a calculator, we can work this out real easy. I don't. So I'll just write down what this is. 10 factorial is 10 times every whole number less than itself. So that's, I'll tell you what, let me rewrite this first. 10 factorial over 7 factorial. There we go. 10 factorial, that's 10 times every whole number less than itself. Seven factorial, 7 times every whole number less than itself. This is a product up top. This is a product down at the bottom. So we can cancel out common factors. 7 cancels with 7, 6 cancels with 6, and so on and so forth. And what do we have left? 10 times 9 times 8. Which is exactly what we got before. 720 possible 1, 2, 3 finishes. By the way, I'm not really familiar with the calculator that we're allowed to use on our final exam. But I'll tell you what, it may actually have this function. Check your calculator and see if it has NPR. The permutation of a set of R elements selected from a set of N elements. Our calculators may have that button. And if it does, that will be an easy way to compute these values. Let's gain some practice computing these things. Now, if we have the NPR button on our calculator, fine, use it. I encourage you to use it if you have it. If we don't, this is what we're going to have to do. We're going to have to say this is 9 factorial over 9 minus 6 factorial. And that's 9 factorial over 3 factorial. And apparently that's not a very big number. I'm shocked. But this is 504 let me just check that. 9 times 8 times 7, 6, 5, 4, 3, 2, 1, over 3 factorial, that's 3 times 2 times 1. Those cancel. See, 4 times 5 is 20, times 6 is 120, times 7, no. Oh. Never mind. I see exactly why that didn't look right. A permutation of a set of 3 elements chosen from 9. This should be a 3 here, not a 6. So that's 9 factorial over 6 factorial, 504. Now let me just make sure that that makes sense. It looks good, but let me just check it out. That's 9 factorial, and here's 6 factorial. Okay. This cancels out of the bottom, that cancels out of the top. And 9 times 8 is 72, times 7 is 14, 49, 50. Yep, okay. I've restored my confidence in myself. Compute the permutation of 6 objects selected from a set of 8 objects. That's going to be 8 factorial over 8 minus 6 factorial. And the numbers that I got when I crunched this, let's see, this is 8 factorial over 2 factorial. So that's going to be 20,160. And let's do this one. This one is an interesting case. We're taking a set of 4 elements selected from a set of 4 elements. And we want to know the number of permutations. Well, essentially, we're just taking the entire set of 4 elements and permuting it. Let's see if our formula works. See, if we select a set of 4 elements from a set of 4 elements, we're selecting the entire set of 4 elements. So this should be the number of permutations of a set on 4 elements. And that's going to be 4 factorial, which equals 24, I hope. Yeah. Let's see if our formula works. Let's see, this is n factorial over n minus r factorial. What are we going to do with this? Let me say this. By convention, 0 factorial equals 1. We didn't talk about 0 factorial, but if we ever have to compute 0 factorial, it's equal to 1. So this is going to be 4 factorial over 1, which is 4 factorial, and that equals 24. Okay. Now that we've done some exercises computing with the NPR formula, well, let's do some applied examples. License plates consisting of 3 uppercase letters followed by 2 digits, and the digits have to be from 1 to 9. That way we don't mistake a 0 with an O. 3 uppercase letters followed by 2 digits, 1 through 9, are created. If repetition of characters is allowed, how many distinct license plates can be created? This is essentially a 5-stage experiment where the numbers that we draw are drawn with replacement. N1, that's the number of ways, or number of outcomes associated with the first stage. We select the first letter. The number of possible outcomes is 10. The second stage, we select the second number. The number of possible outcomes, again, is 10 because we're allowing repetition. And 3, the number of ways the third stage can happen, or the number of outcomes possible for the third stage, is 10. Am I right? No, I think my brain just blew a gasket. And if you're wondering, what the heck is he doing? Good for you, you're paying attention. L1, L2, L3, they're uppercase letters. We have more than 10 uppercase letters, I think. N1, the number of outcomes when we select the first letter, there are 26 possible letters. And repetition is allowed, so the number that, or rather the letter that we select in the first place can also be selected for the second place. So N2, the number of outcomes for selecting the second letter, still 26. N3, the number of outcomes in selecting the third letter, still 26 because repetition is allowed. The fourth stage, we're selecting a digit, 1 through 9. So there's 9 possible outcomes. N sub 5, we're selecting another digit and repetition is allowed. So all 9 digits are still available for the 5th slot. This is a 5-stage experiment. The number of outcomes is just N1 times N2 times N3 times N4 times N5, which equals 26, 26, 26, 9 times 9. I have no idea what that is. Okay, I cranked out the numbers, and this is what we get. There are 26 times 26 times 26 times 9 times 9 gives us 1,423,656 license plates that we can construct in this manner. Okay, let's do this again under a different premise. License plates consisting of 3 uppercase letters followed by 2 digits. And again, the digits just go from 1 to 9, so there are only 9 digits are created. If repetition repetition of characters is not allowed, how many distinct license plates can be created? So here, the letters, the uppercase letters, are being selected without replacement, and the digits are being selected without replacement. So let's see how this turns out. This is again a 5-stage experiment. We select the first letter, we select the second letter, we select the third letter, we select the first digit, we select the second digit. N1, the number of outcomes of the first stage, we're selecting the first letter. There are 26 different letters that can be selected. We select the second letter, and since repetition is not allowed, whatever we selected for the first letter can't be selected for the second. So when we select the second letter, there are only 25 letters to choose from. So there are only 25 outcomes for the second stage of the experiment. And for the third stage of the experiment, when we select the third letter, since we can't have repetition, we can't use either of the first two letters. So we only have 24 letters to choose from for the third letter. Now we go to the digits, the fourth stage of the experiment. We have 9 digits to select from. So n sub 4, the selection of the first digit is 9. But what about the second digit? Since repetition is not allowed, whatever digit we used here can't be selected for this spot. So we've used one of the digits for this spot. We only have 8 digits remaining to be used for this spot. So the number of outcomes associated with the 5th stage of the experiment is 8. And so number of outcomes, or number of distinct license plates that's going to be N1 times N2 times N3 times N4 times N5, and that's 26 times 25 times 24 times 9 times 8. And I cranked this one out ahead of time. 1,123,200. Try that yourselves to make sure you get the same result. But it looks like by allowing repetition in the first case, we got about 300,000 extra license plates. Number of distinct license plates, 1,123,200. Remember that letter. Let's do this in a different way, okay? Let's do this in a different way. Same exercise, but we're going to do it differently. We can view this a different way. We can view this as a 2-stage experiment. The first stage is that we select the 3 uppercase letters. And the second stage is that we select the 2 digits. Now think about this. how many different ways can we select the 3 uppercase letters from a set of 26 uppercase letters if repetition is not allowed? If we're not allowing repetition, then the 3 numbers here can only be used once. So what this is, it's a permutation. Whoops. It's a permutation of 26 letters selected 3 at a time. Or looking at it another way, it's a permutation of 3 letters selected from a set of 26 letters. And that's going to equal 26 factorial over 26 minus 3 factorial. And do I know what that is? I think so. 15,600. Crunch that out on your calculators and make sure that's what you get. Now the second stage, we select 2 digits. Can those digits be repeated? No. So we're selecting 2 different numbers from a set of 9 numbers. That's a permutation of 9 digits selected 2 at a time. Or we can say it's a permutation of a set of 2 digits selected from a set of 9 digits. How many ways can that happen? 9 factorial over 9 minus 2 factorial. And if we grind that out, that's 72. The number of license plates that we can get is N1, number of outcomes of the first stage, times N2, the number of outcomes of the second stage, 15,600 times 72. And if there's any justice in this world at all, it's 1,123,200, which is what we got doing it the other way.